Typical day of Spring Valley soccer practice.
When we come down, oh yeah, 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 we'll be dreaming safe and sound. You better know why.
Man, these home runs are great, but we need more. We're on varsity. We need more of a challenge.
All right, kick this ball through that hoop.
That's for you, Dave.
Not even close.
It is time to train.
51, 52, 53, 54.
Yeehaw!
327, 328, 329. Oh gosh, I'm stuck.
I, Planck's constant, E, pi.
We're going about this all wrong.
Dude, we need some calculus.
Oh, dude, what did D-Stiff teach us last week?
I don't know, something about particle motion?
Particle motion? The first thing that we had to do is measure the distance from our location to the basketball hoop. Google Maps helped us with this, providing us with a distance of 2.04 kilometers. We knew that in order to achieve the maximum distance, the ball should be kicked at a 45-degree angle. With this knowledge, we can model the components of the ball's motion with the equation y equals y initial plus the velocity in the y direction initial times time plus 1/2 acceleration times time squared, and x equals velocity in the x direction initial times time. Solving this tells us that the ball must travel with an initial velocity of 141 meters per second. We use simple trigonometry to break down the velocity vector into its components x and y, which were both 100 meters per second. Plugging the time into the x equation provides us with the total distance that the ball traveled horizontally. By taking the derivative of the y position function, we are provided with an equation for the vertical velocity. The second derivative of the y position function provides us with the y hat acceleration, which is 9.81 meters per second at all times t for this problem, which is the same as gravity. Similarly, the derivative of the x position function provides us with the horizontal velocity, which is 100 meters per second for all times t in this scenario. By solving this equation when y is equal to 0, we found the x-intercept of this graph, which resulted in the hang time that the ball was in the air. The y position function was concave down, which means that the velocity function would have a negative slope and that the acceleration would have a negative value for all times t. Since the x position function is increasing at a constant rate, we knew the velocity would be a constant number for all times t and that there would be no acceleration in the x direction. In order to know how high we needed to kick the ball, we solved for this maximum point on the y position graph. At this point, velocity is 0, so we took the derivative of the y position function to give us the velocity in the y direction. We set this equal to 0 and solve for t, giving us the time at this point. By plugging this time back into the original y position equation, it provides us with the y maximum. This is how high we needed to kick the ball.
So with our calculations, we realized that we needed a greater initial velocity and trajectory. Let's try punting.
Yeah, punting.
Bump squat.
Yeah, I'm pretty good with balls.